The question that I have here is, how do you calculate shear flow in built-up beams? Let's try and understand the fundamentals first. It's always easier if you start with something simple. So first I'm going to take a beam with a rectangular cross-section. Because of two-way symmetry, the centroid C of this rectangular cross-section is going to be right in the middle. I have placed the y and the z axes right at the centroid C. The beam is subjected to a shear force V in the y direction and a bending moment M above the z-axis like shown in this picture. So what is shear flow? Well, shear flow, and we'll call that little q, is the shear force per unit length along the x-axis. Here, x-axis is taken to be along the axis of the beam. Without getting into the details, if you recall the way we came up with the shear formula, this is what we did. We carved out a little rectangular prism like this, drew the free body diagram for it, and wrote down a force equilibrium equation in the x direction like this. And here F1 is the force due to the bending stresses acting on this shaded area. F2 is the force due to the bending stresses acting on this back face. And this boundary is free. 1, 2, 4, 3 is a free surface. And similarly, this rectangular surface on the other side is a free surface. And this top rectangle is also a free surface. And this delta H is the force acting on this rectangular area on the rectangular prism. And obviously there is an equal and opposite force acting on the bottom part of the beam. Since F1 and F2 are not equal to each other, there's a need for this force, delta H, in order to maintain force equilibrium, right? Alright, then we went through a little bit of analysis to show that delta H equals VQ times delta X over I. The shear flow, little q, which is defined as the shear force per unit length along the x-axis. So it'll be delta H over delta X, which works out to be VQ over I, right? And Q here is A prime, which is the area of the shaded part, multiplied by Y bar prime, which is the distance, the centroid of the shaded area from the z-axis, right? What if we have a T-beam like this? Well, the analysis is going to be similar, right? So the shear flow, which is the force per unit length along this rectangular surface, which is the surface between the flange and the web, is still given by this equation. Little q equals VQ over I, where Q is the product between A prime and Y bar prime, where A prime is the area of this shaded part, which is basically the area of the flange, multiplied by Y bar prime, where Y bar prime is the distance, the centroid of this shaded area from the z-axis, where z-axis is placed right on the centroid of this T-beam, right? So if this T-beam is built out of two boards like shown in this picture using nails, then we will need to know the shear force, right, per unit length on that interface between the flange and the web, right? So this is how we would calculate that force. Once we calculate a value for little q, we can then design the details of the nails. Like for example, given the strength of a single nail, we can calculate the spacing between nails, right? Now let's consider a box-shaped beam like shown here, where 4 boards are used to construct the beam using nails. But here the nails are driven in sideways like shown in this picture. To design the details of the nails, we need to know the shear force that acts between this vertical board and the horizontal board. In other words, on this vertical plane. The approach for deriving the formula for the shear flow is basically the same as before, except for the way that we cut out this rectangular prism. These two pictures shows exactly the way we cut out the rectangular prism. We basically cut out this inner part, not the whole thing. This line doesn't extend all the way to the surface here. It only includes this part of the board. Because of the bending moment M, these forces F1 and F2 are still going to be different from each other, and there needs to be a force to balance the difference, right? But this time, this horizontal surface and that horizontal surface are both free surfaces, so there cannot be forces on those, right? So the force to balance the difference between F1 and F2 will have to come from these vertical rectangular faces. And that's exactly what we are seeking to find in order to design the nails, right? The formula is still the same. Little q equals VQ over I. But of course this Q now consists of the force on this side plus the force on that side. Okay, so to design the nails on one side, you're going to have to take half of this. Also, take note of the way capital Q is defined. Capital Q is defined as A prime times Y bar prime, where A prime is the area of the shaded part. In other words, area of the board inside here. All right. Y bar prime, of course, is the distance, the centroid of the shaded area from the z-axis. So now we put Q over 2 on this side and Q over 2 on the other side. So this might look a little strange to you because we are calculating the force on the vertical plane, not on the horizontal plane, right? But don't worry, we are using the fundamental principle of equilibrium. So this is how you calculate the shear flow for built-up beams in order to design whatever that is holding the boards together. It could be nails, it could be glue. So here's a little summary of what we just talked about for the T-shaped beam and the box-shaped beam. Here are two more examples of how you would calculate the shear flow little q in order to design the nails that are holding the boards.